Last episode, every single call we made, REST, SOAP, gRPC, all of it, ended up at the same glowing box. We never opened that box. Today we do because at 8 pm Dabba's orders are about to find out exactly what's inside. So what actually is a database? Not the mystery box, the real thing. At its simplest, it's just organized storage that remembers things correctly, even when 1,000 people ask at once. Remembers correctly is doing a lot of work in that sentence. That's where today's story actually starts. Think about the bill counter at a busy restaurant, not the kitchen. The counter where the order actually gets written down. The person there doesn't scribble fast and hope for the best. Table for 1 plate, exact price, in order, written once. Because if this line gets it wrong, someone gets billed for someone else's biryani. That carefulness or poem-piece, writing things down exactly right in order, no skipping, is what a database actually does. This is the bill counter. Remember it because it's coming back. Zoom out from one order and you get a table. The bill counter's full ledger. Every page shaped the same way. Every row has to fit those same columns. No row gets to skip the price. No row gets an extra column just because today felt creative. That rigid shape has a name. SQL, Structured Query Language. And it's run banks, airlines and government records for 50 years for one very good reason. And it's not just one ledger, it's several, all linked. Look at Dabba's real setup. The orders table doesn't repeat your name and address on every single row. That would be wasteful. And worse, if you moved house, you'd have to fix it in 1,000 places. Instead, an order just points at a customer by ID and points at a restaurant by ID. One source of truth, everything else just references it. That's what makes it relational. Here's why the bill counter is so careful. And it's not paranoia, it's this. Watch a payment happen. Money has to leave your account and the order has to confirm. Both or neither. If the app crashes exactly between those two steps, you can't end up having paid for nothing or gotten food you never paid for. It's called a transaction. And the rule you just watched is only one letter of a 4-letter promise called ACID. Consistency means every rule still holds after the write. No order ever gets saved without a customer attached to it. Isolation means two orders happening at the exact same instant. Never see each other's half-finished work, even on a busy Saturday night. And durability means the second a payment is confirmed, it survives. Even if the power actually goes out 1 second later. That's the exact promise UPI relies on millions of times a day. All 4 letters, every single transaction. So SQL keeps you safe. But that same rigidity has a cost, and it shows up the moment your app grows up. Add one new column to a table with 10 million rows, and every single one of those rows has to be touched, checked, rewritten. On a small app, that's instant. On Dabba's scale, that's a maintenance window everyone dreads. The shape that keeps you correct is the same shape that makes you slow to change. Before we leave SQL behind for a bit, quick roll call because you'll see these names constantly. MySQL, PostgreSQL, Oracle, SQL Server. Different companies, very different personalities, but every single one speaks this exact same relational shape. Tables, rows, columns, ACID. Postgres is the precise open source favorite. Oracle quietly powers half the banks on earth. MySQL runs a shocking amount of the ordinary web you use today. Learn the shape once and you can read almost any of them. Now picture something SQL was never built for. Dabba's restaurant catalog, where every restaurant is wildly different. The biryani place needs a spice level field. The bakery needs eggless, yes or no. The juice stall needs sugar percentage. Force all of that into one rigid table. And you get 500 columns, most of them empty. SQL is the government form Same fields every time for everyone. What this catalog actually needs looks more like a diary. Write down whatever this entry needs, nothing more. The diary idea has a real name, a document store, and it's the most common shape of NoSQL. Each record, each document carries exactly the fields it needs and not one more. No shared column list forcing every restaurant into the same box. Add a new field to one restaurant tomorrow and nothing else in the whole catalog even notices. Document stores aren't the only shape NoSQL comes in. Three more quickly. Key value stores are a giant lookup dictionary, perfect for a session token or a card. Wide column stores handle huge, sparse data at scale. Graph databases care about the connections themselves. Who's friends with who ordered from where. Different shapes, same spirit. Bend the storage to fit the data, not the other way around. And same roll call for NoSQL. Because NoSQL was never one thing, it's a whole family of specialists. MongoDB is the classic document store. It reads almost like writing plain JSON. Redis is a key value store so fast it's often used just as a cache. Cassandra handles wide column data at a scale that survives entire data centers going down. Facebook built it for exactly that. And Neo4j lives for graphs, for connections, for who knows who. Different shapes, different specialists. Pick the one that actually matches your data, not the other way around. Nothing here is free, though. NoSQL trades something away for all that flexibility. There's no built-in connect these two things and check they match, the way SQL's relationships do. And when you have many servers holding copies of the same data, they don't always agree the instant something changes. They catch up a moment later. That's called eventual consistency. And whether that's fine or a deal breaker depends entirely on what you're storing. We'll open that whole can of worms properly later in the season. And that flexibility buys you something SQL has always struggled with: scale. Traditionally, when a SQL database outgrew its machine, the answer was simple and expensive: buy a bigger machine, scale up. NoSQL was built from day one assuming you'd add more ordinary machines side by side and split the data across them. Scale out. Neither is better. They're built for different growth curves. And we'll live inside both of those curves later this season. So, before the scorecard, how do you actually decide this in the real world? Three quick questions. Does this data need to be exactly provably correct like money? Lean SQL. Does the shape of your data change all the time, or do you need to survive massive, unpredictable scale? Lean NoSQL. One more. Do you need to search across everything at once, joining pieces together? That's SQL's home turf. NoSQL makes you do that stitching yourself. And if you're genuinely not sure, start with SQL. It's the safer default and you can always split off a NoSQL piece later, the way Dabba actually does. Let's put both of them on one board, because side by side, the choice gets obvious fast. Fixed shape, strong guarantees, built-in relationships. That's SQL's whole personality. Flexible shape, looser guarantees, built for spreading wide. That's NoSQL's. So, which one does Dabba actually run on? Trick question. Both, each exactly where it earns its place. Orders and payments live in SQL. Every rupee exactly right. Every transaction complete or fully undone. Bill counter territory, no shortcuts. The restaurant catalog, menus, reviews follow you. All of it lives in NoSQL. Millions of reads, wildly different shapes, and it's fine if a new review takes a beat to show up everywhere. One app, two databases, two different jobs. That's not indecision, that's the right answer. So, SQL or NoSQL, the honest answer was never a holy war. It's just what breaks if you're wrong. Get your money wrong, and SQL's strictness saves you. Get your catalog too rigid, and NoSQL's flexibility saves you. Most real systems like Dabba need both. But here's the next problem waiting for us. You picked the right database. It now holds 1 billion rows. So how, in a fraction of a second, do you find just one? Next episode, indexing, finding one row in 1 billion.